So in this video we will learn the proof of the theorem that every differentiable function is continuous but the converse is not true. That means every continuous function is not differentiable. So I am writing the theorem from the Rudin's book. It is in formal form. Let f be defined on AB if f is differentiable at a point x in AB, then f is continuous at x. F is continuous at x. And second part, give an example to show that the converse of the above statement is not true. That means every continuous function is not differentiable. We need to give an example to show that every continuous function is not differentiable. Now to prove the theorem, what we will do, first draw a graph. Like suppose this is x-axis, this is y-axis, and we have a function. Suppose this is f, and suppose we have a function, this is f, and this point is A and this point is B. Consider a point x between A and B. Suppose this is x, so x is here, and it is given that this function f is differentiable at x. Okay, at this point the function is differentiable. It is given. We need to show this function is continuous at x. Now from the definition of continuity, so proof from the definition of continuity we know that a function f is continuous at a point x if limit of t approaches x, f of t equals to f of x. Okay. That means if you consider a variable t, and if t approaches x from left or from right, then the f of t would be same as f of x. Now as t approaches x, we have limit of t approaches x, f of t minus f of x equals to, we can rewrite this one as limit of t approaches x, f of t minus f of x over, so I am multiplying by 1, that means I'm dividing by t minus x first and then multiplying by t minus x. So those two will cancel and we'll get back the same thing. Now this can be written as limit of t approaches x f of t minus f of x over t minus x times limit of t approaches x t minus x, because we can distribute the limit sign. Now from the definition of differentiability, this part is a prime of x from the definition of differentiability. So this one become a prime of x, and the derivative exists. It is given in the theorem that the function is differentiable, that means derivative exists, and when t approaches x, so this become x minus x, that means times 0, it becomes 0. So if you multiply, this is 0, that is limit of t approaches x f of t minus f of x equals to 0, and this one can be written as, so limit of t approaches x f of t equals to f of x. Okay, because this is x, so there is no contribution of limit for this one. So limit of t approaches x f of t minus f of x would be 0, and if you take f of x on the right side, then you will get this one. Okay, so this is what we need. Okay, so therefore the function is continuous. Okay. So we proved the first part of the theorem. Now we need to give an example to show that if a function is continuous, then it may not be differentiable. So the following example shows that every continuous function is not differentiable. At a point. Okay, so let f of x equals to absolute value of x. Okay, absolute value of x. So if you draw the function absolute value of x, then it is like that. So this is x-axis, so this is x-axis, this is y-axis, sorry, this is y-axis, this is x-axis, and y equals to absolute value of x, its graph is like this. Okay, this is y equals to absolute value of x. This function is not differentiable at x equals to 0. At x equals to 0, so at x equals to 0, the function y equals to absolute value of x is continuous, but not differentiable. Why not differentiable? Why not differentiable? Because from the 0, if you move little bit right, then the slope of the function is positive. If you move little bit right, then slope is positive. And if you move from little bit left from 0, then slope is negative. Okay, so if you move little bit left, slope is negative, but if you move little bit right, slope is positive. That means left hand derivative and right hand derivative are not same, so the function is not differentiable at x equals to 0. Thanks for watching.